All right, ladies and gentlemen, this is the fundamental theorem calculus. Not part 2 this time, but part 1. This is a very important piece of the puzzle to understand. It's not fairly complex. I'll break it down in the layman's terms, but this is the reason why we can look at an antiderivative and say it's an integral and say that it undoes it. Okay, so let's check it out one step at a time. This is what the fundamental theorem of calculus part 1 says. So it says if f is continuous on an interval a to b, so oops, let me draw it back some. We already talked about on other videos that we've discussed it's the area up to a certain point. So if f is continuous, so here's f, there's f, beautiful little f, on some interval a to b, okay? Then a function g can be defined. Now what does the g function do? Well, we call him the area under the curve. And why is g the area under the curve? Because he's integrating up to some number x. So if I wanted g of 3, that would be go up to the number 3. That's in between a and b, obviously. And then give me the area from a to that number 3. So that's exactly... it's x really though. That's based off of this x value, right? Which is the top bound. So it allows it to travel and pick up as much area as it wants starting at A. So we want x to go to B eventually. And that means that it's got to be continuous in order for this to happen. This is number 1. It's got to be differentiable, because how the heck can we look at a antiderivative if there is no derivative? And then you know that if you take the derivative, and this is the big piece, if you took the derivative of g, and this is the part that really makes the fundamental theorem of calculus part 1 a big deal, is that this ends up giving you just f. Okay, because they should, because the relationship is that g is the integral of f. So to get back to f from g, you would have to take the derivative. So the way you want to think about this, just to draw you another diagram, if that wasn't confusing enough, f is the original function. G is the original, is the antiderivative. So when if you wanted to get back to f, you would have to take the derivative to get there, right? And if you want to get f back to g, you would have to take the antiderivative to get there. Okay, it's always hard. I always like anti coming back, but the idea is that the relationship is one and the same. You got to know when to integrate and which way is the direction. Which one way I'm going to take the derivative, the other way I'm going to take the integral. So be very, very careful here. All right, so we already talked about finding values of areas under curves. So I'm going to approximate this one. Okay, so I'm going to show you that every area is not beautiful, and this is why integrals are just so powerful. If you look at this guy, they want the area starting of g of 3. So g of 3 would be some area a to 3. Well, we're going to, from here it's 0. That's where 0 is, up to number 3. So that's like all of this area, and then see this curvy area. That's a pain in the butt because I don't know what the function is. And that's where it can only be approximated. And that's the big thing. I can't find the exact value. So g of 3 is approximately, looks like 1/2 base times height. This is 1. This is 2, right? Base is 1. That's 2. Okay, easy. And this can be, looks like it's bigger than 1, like 1.5-ish. So that lets me know this is approximately going to be this. So my point is that this goes back to the Riemann sum. If you don't know exactly how to find the integral, the best you can do is approximate it. Okay? So, but we always want to make sure we know how to find the integral for stuff we're qualified for. So g of 3 was no good, so in terms of perfection, but it'll work. 4.5-ish, high end force. All right, so let's say they say find the derivative of this guy. Okay, and here's g of x, and this is how they define g of x. So everybody pay attention to this birdie. So that means if I take the derivative of g of x on both sides, whatever I do to one side, I'm going to do to the other side. Well, we just figured out that when I hit a derivative of g, right, this thing ends up being just regular old f. But then what is f? Well, the derivative and the antiderivative going up to x ends up being this blob. So that ends up being square root of 1 plus x squared. And that's kind of what the point is that the rates of change undoes the net change, and then you're left with just the function. They undo each other. It's actually kind of cool. They are inverses. They undo one another. Okay, let's keep it going. Okay, how about this guy? I think this is the guy we just did, isn't it? I think it is. I think I will do one more though. Okay, how about this guy? Let's say that it said to take the derivative of this, but I'm going to make this guy on top. Oops. Top's a little trickier, and this will prompt us for the next video that we have. Alright, let's make this guy 3x instead. Alright? So you say take the derivative, you say, right? And I'm like, okay. Well, how do I go about approaching this? And this will get us to our next video. Okay, if I take the derivative of this guy, well, what does this normally mean? Okay, so let's just talk about this. I'm going to take the derivative of this. I'm going to take the derivative of this. Hold on, but does this really, really mean that they just undo each other, Rush? The real answer is kinda. So watch this. Let's pretend we knew how to do this integral, right? And I'm going to call it happy face. So this should end up giving us the derivative, which is h prime. Okay. Does this really undo each other is the question. So maybe let's not worry about what's on the side. Does it really undo each other? Well, let's see what happens. If I were to just follow order of operations, you would first tell me to do the derivative, the integral of this. And then you would get some magic function, right? Big F, okay? And then big F of x, you would need to input in 0 to 3x. This is standard, right? Standard stuff. Which means that we'd thus have to take the derivative. And this is the big point. In the next video, I'll go into this in even bigger detail. Of this. But hold on a second. You already know, and this is the big key here. Maybe I should have saved it for the next video. You want me to take the derivative now. So I just took the integral. I don't know what the exact function was, but I did figure out that the net change would be this big F, which I don't know what it is exactly. Minus of when I plug in 3x minus f of 0. Now, check out what happens when I take a derivative. This is just a constant because it goes into a function, so it's going to end up being 0. It's going to be a number. When I take a derivative of a number, that'll be 0. So that's easy. It really comes down to taking the derivative of this thing. But hold on. This is going to require chain rule. So when you take the derivative of this, well, it's going to be the derivative of the f function. And then, right, the entire function, the inside function is 3x though. So, but what's the derivative of the big f function, the big antiderivative function? That guy, the guy that's the derivative of the net change, the antiderivative guy, is just going to be regular old little f times 3. So, moral of the story is that this will be 3 times the square root of f of 3x. What was f of? F is this guy. So that ends up being f of t plus 3, 1 plus 3x squared, which ends up giving me 3 times the square root of 1 plus 9x squared. Okay, so bottom line is that the fundamental theorem of calculus, literally part 1, lets us able to talk about what happens if my bounds are changing 3 times as fast instead of just at one simple rate. But we'll talk about this in many different examples. This is a great lead-off question for our next video. All right, guys, I will see you on the next video, Fundamental Theorem of Calculus, Part 1. Bye.